Let's look at OpenStax College Physics, Chapter 17, Problem 43. If a wind instrument, such as a tuba, has a fundamental frequency of 32 Hz, what are its first three overtones? It is closed at one end. The overtones of a real tuba are more complex than this example because it is tapered tube. So let's write down the things that we know. We know that the fundamental frequency, so F1, is 32 Hz. And we're looking for the first three overtones. So we want F, I don't even know how to write this. I'll just say first three overtones. So why don't I know what it is that I'm looking for? Well, here I have a diagram for a tube that's closed at one end and open at the other. So closed at one end means that there is a node there. Open means that there is an antinode. So closed, open, closed, open. And this is the fundamental frequency. So I know that that much is a quarter wavelength. So I have a lambda over 4 over here. Then if I look at the next pattern, I know that that is 3/4 of a wavelength. And then the next pattern is 5/4 of a wavelength. So let's look at that again. So I'm going to start with the last one because I know that this much is a full wavelength. So that is a full wavelength. That means that only that much is a quarter wavelength. So in the first pattern here, that's all I'm seeing. That's 1/4 wavelength. Then here I have 1/4, another quarter, and a third quarter. So that is 3/4 wavelengths. So that's where the 1, 3, and 5 come from. So now I can go back to this part where I said I don't even know how to write this, because first three overtones means different things if we have a tube that's closed at one end and one that's open end, or if it were open at both ends. If it had been open at both ends, we would have had an antinode at both ends, so we would have had different equations for that. So the fact that I know that the length accommodates a quarter wavelength, 3/4 wavelengths, or 5/4 wavelengths mean that my overtones are for n equals 3, 5, and 7, not 1, 2, 3, 4, and so on. So the equation here, let's just derive it. It's not hard to derive. So I know that lambda over 4 times some number, some odd number, is equal to L, which means that lambda is going to be 4L divided by N. But we know that the speed of sound is lambda times frequency, so frequency then is V over lambda. So frequency for the nth overtone or nth harmonic is going to be NV over 4L, where N is an odd integer, 1, 3, 5, and so on. So this is the equation for a tube open at one end and closed at the other. So that's why the first three overtones are N equals 3, N equals 5, and N equals 7. So all I have to do to figure out these F's, so F sub N is going to be 3 times F1, F sub 5 is going to be 5 F1, and F sub 7 is going to be 7 F1. So then this is 32 times 3, and that's 96 Hertz. This will be 5 times 32, and that's 160 Hertz. And then the last one is 7 times 32, and that is 224 Hertz. So Here we have the first three overtones for sound that has a fundamental frequency of 32 Hertz, and it's in a tube that's open at one end and closed at the other.